Okay, today we will discuss about the filter banks and discrete wavelet transform DWT. What we have studied till now is the multi-resolution formulation of wavelet systems, and in that we have studied that we start from a scaling function phi t, and the scaling function must satisfy this refinement equation, or what we see it as multi-resolution equation, that the scaling function should be expressed in terms of scaling function or the scales and dilates. Okay, so it was something like this: phi t is equal to square root of 2 h naught n phi of 2t minus n, and then from this scaling function we generate a wavelet function psi t, and psi t is also expressed in terms of scaling function h1n phi of 2t minus n summation over n. Okay. And based on these two equations, we have decomposed a function. A function can be decomposed in terms of scaling functions and the wavelet functions at different scales and translates. So we generally use a single scaling function, that is, we have coefficients ck multiplied with phi of kt, and then rest are the wavelet functions. So you have d of jk multiplied with psi of psi jk of t. Okay, this is the wavelet expansion of a function f t in terms of the scaling function. So for this we have taken scale j is equal to 0. So we choose a scaling function at 0 scale, and we choose wavelet functions at different scales and different translates. Okay, so by combining these scaling functions with different coefficients, and then by combining the wavelet functions with different coefficients, you can decompose the signal in this form, which is the DWT. So these coefficients basically they form the discrete wavelet transform for this signal f of t. Okay, and based on these two equations, refinement equations, we have seen that okay, these equations h0n and h1n, they are basically a filter. So the solution for this equation, it may or may not exist. Okay, if it exists, it must be unique. And for Haar system, we have seen that these coefficients are 1 by root 2, and we have two coefficients, 1 by root 2 and 1 by root 2. And similarly for the Haar wavelet, these coefficients are 1 by root 2 and 1 minus 1 by root 2. Okay, so this we call as scaling filter, and this we call as the wavelet filter. Okay, so you will see that many a times you need not to know about the scaling and the wavelet functions or the shapes of these functions. What we are interested in basically the relation between these filters, that is h01 and h1n, and the expansion coefficients, that is ck and d of jk. Okay, so in order to develop that relation, this discrete wavelet transform is basically implemented using a filter banks structure. Okay, and the basic idea in that is that that you will see that these expansion coefficients at a higher scale, or in fact at a lower scale, they can be obtained from the expansion coefficients at a higher scale. Okay, it means if you know these coefficients for scale j, from this scale you can find the coefficients at scale j minus 1, and similarly detailed coefficients at scale j minus 1. Okay. Similarly, if you have the idea about the coefficients at scale j minus 1, you can get the coefficients, the approximation and the detailed coefficients at a scale of j minus 2, and similar detailed coefficient at scale of j minus 2 and so on. Okay, so if you start from any scale, any higher scale or higher resolution, the lower resolution coefficients, expansion coefficients, they can be obtained from these coefficients using a filter bank. Okay, so there is a direct one-to-one relation between now these expansion coefficients and these filters, scaling and the wavelet filters. Okay, so we basically forget now the scaling and the wavelet functions, right? So there are two different approaches to basically understand DWT. One is using the filter banks, and one is using this expansion of a function in terms of scaling and the wavelet functions that we have already discussed. Okay, so we will discuss now this DWT and filter banks. So to develop this relation, we start from the basic refinement equation phi t summation of under root 2 h naught and phi of 2t minus n. Okay, so from this phi t you can generate phi of 2 to the power jt minus k. Okay, so if you generate this function phi 2 to the power jt minus k from this phi t, so it will become under root of 2 h naught and phi of 2 into, now t will become your 2 to the power j t minus k minus n, and you can write it as under root 2 h naught and phi of, if you multiply this with this, you'll get 2 to the power j plus 1t minus 2k minus n. Okay, or you can write it as minus of 2k plus n here. Okay, and if you replace this variable 2k plus n with n, if you replace 2 plus kn with a variable n, you can write this equation as under root of 2 h naught of n will become m minus 2k phi of 2 to the power j plus 1t minus n. Okay. Okay, we have seen that if the scaling and the wavelet functions, if they form a orthogonal set, in that case, these coefficients cjk, they can be obtained as the inner product of this function f of t with the scaling functions. Okay, this function is basically phi of jkt, and if you find the inner product of this function, it will become f of t multiplied with this function, and this function will be 2 to the power j by 2 phi of 2 to the power j t minus k into dt. Okay, so this factor we have used just to maintain the norm that we already discussed, why we use 2 to the power j by 2. Okay, so to maintain the norm of this signal phi j k t at every scale, it will maintain the norm. Now in place of this, if I use this equation and if I put this into this, what you will get? You will get phi of t, f of t, 2 to the power j by 2 multiplied with this equation, that is summation of under root 2 h naught m minus 2k phi of 2 to the power j plus 1t minus m into dt. Okay, and if you arrange this order of integration and summation, So you can write it as under root of, or you can write it as h naught m minus 2k. This under root 2, if you multiply this with 2 to the power j by 2, so under root 2 is basically 2 to the power 1 by 2. Okay, so if you multiply these two factors, you will get integration of f of t 2 to the power, it will become j plus 1 by 2. Okay, this and this combined, then multiplied with phi of 2 to the power j plus 1 t minus m into dt. Now if you look to this integral, what is this? This is the inner product of the function with a scaling function at a scale of j plus 1. It means this will give you the coefficients at a scale of j plus 1. Okay, so or you can write that because Cj is basically nothing but summation of h0 m minus 2k into c of j plus 1. Okay, and similarly these coefficients, the detailed coefficients that we get d, j, k, again it will be defined by the product of the function with the wavelet functions. Okay, and the wavelet functions can also be expressed using a refinement equation like this. Okay, so you have the same procedure. Ultimately you will get equation like this. Now in place of h0, your filter will be h1 only here. Everything is same. So it will be h1 of m minus 2k into c of j plus 1. Okay. So these two equations, and if you interpret these two equations, what these equations are basically, yeah, one equation, okay, Cj is equal to summation of h naught m minus 2k into c of j plus 1. In the second equation you have dj is equal to h1 m minus 2k c of j plus 1. So this equation gives you the coefficients, expansion coefficients, that for the scaling function basically Cj at a scale j, they can be obtained from the coefficients at a scale j plus 1 using the scaling filter. And similarly, the detailed coefficient at scale j can be obtained from the scaling coefficients at j plus 1 using the wavelet filter. Okay, so if you interpret this equation, what it actually is, see if you look to this equation, how we implement this equation, it is nothing basically but equation of convolution with a downsampler. Okay, if you see the equation of convolution in discrete time filters, you have a signal xn passing through a filter with some impulse response hn. So you get output sequence yn, where yn is the convolution between x and h. That is, it is h of n minus k into x of k summation over k. Okay, so you basically fold one sequence and you shift it, multiply with other, add, and so on. You get y0, then y1, y2, and so on. Okay, and after this, if you downsample this sequence by a factor of 2, if you pass this through a downsampler, this is a downsampler. Okay, downsampler means that if you pass a sequence xn through a downsampler, it will generate a sequence x of 2n at the output. Okay, it means it will discard one sample from the input sequence. So you will have here x0 only, then x2, then x4, x6, and so on. So one sample will be deleted if you pass a signal through downsampler, or we call it the decimator. Okay. So if you replace n with 2n, if the output of the convolution or this filter is passed through a downsampler, you will get h of 2n minus k into x of k. Okay. So this sequence is now very much similar to this output. It means it is, in place of xk, you have this sequence c of j plus 1. Output is your cj, and how you get this output? You are passing this cj plus 1 through a filter h0 n. In fact, h0 of minus n here, because it is minus 2k here. It was 2n here, then it was 2n. It is minus, it will become h0 of minus n as the impulse response. And then you pass it through a decimator by a factor of 2, you will get the output sequence. Okay, so the filter bank implementation for this is that if you have these coefficients c of j plus 1, so you pass it through a discrete time filter with impulse response h0 of minus n, and then you decimate it by a factor of 2, you will get here cj. Okay, so the lower resolution coefficients are basically obtained from the high resolution coefficients using a filter structure. And similarly, this dj, if you pass now this signal through another filter, which is a wavelet filter now h1 of minus n, and again decimate by a factor of 2, you will get detailed coefficient at scale j. Okay, so we have omitted this wavelet and the scaling functions in this case. So we have a direct relation between the expansion coefficients and these filters. Okay, so this you can, now this structure will continue. Okay, so we start from a scale suppose j plus 1. So by passing this through a series of filters h0 of minus n, h1 of minus n, this is scaling and the wavelet filters, and then decimate by a factor of 2, you will get scaling expansion coefficients at scale j and detailed coefficient at level j. Okay, then this cj, it can be again decomposed. You can again pass this expansion coefficients through the same filters, that is h0 of minus n and h1 of minus n, and downsample by a factor of 2, you will get these coefficients at a lower scale, that is c of j minus 1 and d of j minus 1, and so on. So this c of j minus 1 can be further decomposed, and we can get cj minus 2 and dj minus 2, and so on. Okay, so this is a tree-like structure basically. Okay, so we start from the scaling filter coefficients. This is for the scaling expansion coefficient, function expansion coefficients, or we call it approximate coefficients, and dj, these are called as detailed coefficients. Okay, so start from approximation coefficients at any scale, and then you decompose this into detailed coefficient at the next lower scale and the approximation coefficients at the next lower scales. Then the cj is again decomposed into d of j minus 1 and c of j minus 1. So this is further decomposed into c of j minus 2 and d of j minus 2, and so on. Okay, so this tree-like structure is a very important algorithm in the wavelet, which is called as Mlat's algorithm. Or we also call it as subband coding. Okay, Now you can weave this structure in the sense of filter banks only. In fact, there is nothing about the scaling and the wavelet functions. Okay, so many people they look to this wavelet theory into different aspects, either in terms of expansion of a function in terms of wavelets and scaling functions, or in terms of a filter banks. Okay, now once you decompose like this, then of course in relation with this is what is called as analysis. Okay, analysis filter bank. So you go from fine scale to coarse scale. That is, you go from high resolution to lower resolutions. Okay. And of course, when you have this, when you have to reconstruct this, or when you have synthesis filter bank, you go from coarse scale to the fine scale, and you have a reverse process for that. So start from the scaling and the wave, these approximation and the detailed coefficients at a lower scale, and you combine them together to get the approximation coefficients at a next higher scale. Then there is coefficients, approximation and detailed coefficient at this scale, they are again combined to get the approximation coefficients at the next higher scale, and so on. That is a reconstruction algorithm. Okay, so now in terms of the filters, if you look to this, what basically you are doing, so you are processing these coefficients at a scales. Suppose you start from Cj plus 1, so you pass it through two filters, H0 of -1 and H1 of -1, and decimate by a factor of 2, you get Cj and Dj. So output of wavelet filter will give you detailed coefficients, output of scaling filter will give you approximation coefficients, and then these are further decomposed like this. Again we have H0 of -n, H1 of -n, decimation by a factor of 2, you get Cj -1 and Dj -1, and so on. Now these filters, if you see the frequency response of these filters, like for Haar case, your H0n, it was 1 by root 2 and 1 by root 2. You have only two filter coefficients. And H1n, it was 1 by root 2 and -1 by root 2. So from the frequency response point of view, if you look to these filters, it is a low pass filter, because its impulse response is symmetric, and since it is antisymmetric, it will be a high pass filter. Okay, it means when you pass this sequence Cg plus 1 through these filters, these two filters, what they do basically in the frequency domain, they decompose the spectrum of this signal into two equal halves. Okay, they decompose these filters into two different halves. So you have in the terms of frequency response, these two filters, they have frequency response like this. If you say it is ideal filter, so it is 0 to pi by 2 and pi. So 0 to pi by 2, its gain is 1. This is the frequency response of this, and pi by 2 to pi, it is 1, and 0 to pi by 2, it is the frequency response of this. Okay, but practically it will not be like this. You will have a filter suppose like this, and another filter you have, which is a high pass filter, it will be like this. So this is your H1 omega, this is your H0 omega. Okay, so they basically split the spectrum of the signal into two parts, into low frequencies and high frequencies. So these are the low frequency components, and these are the high frequency components. Okay, and in the theory of filter bank, we call these filters, that we may discuss one lecture on that, we call it as QMF filters, quadrature mirror filter banks. Okay, or perfect reconstruction filter banks, PR filter banks. Okay, so because the frequency response of the two filters, that is the mirror or the mirror image of each other around this quadrature frequency, that is pi by 2. Okay, so this is first step. So Cj plus 1 is decomposed into Cj and Dj. So in the terms of frequency, the spectrum of this is divided into two halves, low pass and high pass. Now at next scale, what you are doing, you again passing this Cj. It means this spectrum, low pass filter, is again passed through two filters. So at the next scale, it is decomposed into further two parts. So your high pass filter, it will remain the same. This is pi by 2 frequency. This is pi. Now this low pass spectrum, which is basically for Cj, it is again decomposed into low and high frequencies. Okay, so it will be further decomposed into two parts. So you will have one low frequency component and another high frequency component. Now this frequency will be pi by 4. Okay, at next scale, now this low pass spectrum is again decomposed into two parts. So you will have a frequency response like this and two more filters. This will be pi by 8 and so on. Okay, or in terms of the signal spaces that we have discussed, if it is up to level 3, suppose you decompose up to level 3, so this will give you the space of V0 scaling functions. Okay, so ultimately you have only one scaling filter and rest are basically the wavelet filters. Okay, so wavelet filters, they will span this spaces W0, W1, W2. Okay, so some functions, they will be, which are in the space of V0, they are basically covered by this low pass function, low pass filter. So at the end you are left with a one low pass filter and the rest are basically band pass filters. Okay, so these low pass filters, they corresponds to your scaling function, and the band pass filters, they corresponds to your wavelet functions. Okay, and that is why we say when we have wavelet, we have said that okay, the average value of the wavelet must be 0. If the average value of 0, it means that 0 frequency, its spectrum is non-zero, so it cannot be a low pass filter. The spectrum of the wavelet is like a band pass filter. Okay, so we have a basically series of filters which decompose this spectrum into different bands. Okay, so output of this is pi by 2 to pi. Sorry, this is pi by 2 to pi, and this is 0 to pi. Okay, then we need further decomposed of this 0 to pi by 2. Sorry, the 0 to pi by 2 is further decomposed into two parts. So it is 0 to pi by 4 and pi by 4 to pi by 2. So this is a band pass filter. Next scale, now this 0 to pi by 4 is again further decomposed into 0 to pi by 8 and pi by 8 to pi by 4. So different bandwidths you have. So actually what you are doing using this filter bank, you are decomposing the bandwidth of the signal into different segments. So you first decompose into the low pass and high pass components, then these low frequencies are further decomposed into low and high frequencies and so on. So ultimately, finally you have only one scaling filter and rest all are the wavelet filters. Okay, so the scaling filter is a low pass filter and rest of the wavelets, they constitute a band pass spectrum. Okay, this is how we decompose the entire spectrum of the signal into different frequency bands. Okay, so this can also be achieved using another structure like this, but that we study when we use basically when we study filter banks, not wavelets. So you have a signal, you decompose this into a low pass spectrum that is 0 to Here low pass filter first, one output will be now 0 to pi by 8. So it is a low pass filter with this band pass. Another will be a band pass filter, it will be pi by 8 to pi by 4, then pi by 4 to pi by 2, and then pi by 2 to pi. So this structure can be implemented using this also. But in this case, the problem is that we have different filters with different cutoff frequencies or band passes, and as a result, the decimation that you will use after this, that will be different. Decimation factors are different. But in this structure, you have a uniform structure. You have the same filters and the same decimation factors. So you go on decomposing a signal into different bands using this. Okay.